Hello students, welcome to MEMONEET. This is Ravikant, a physics teacher, and today we are going to discuss a topic that is ray optics, right? So today we are going to talk about ray optics. So it will start with two major phenomena which light undergoes. That is, one is reflection and another is refraction. In reflection, what happens? The light ray get incident on a reflecting surface, strikes on it, returns to the same medium from which it was coming. The another phenomena is refraction of light, in which the light ray passes from one medium to another, and while passing through from one medium to another, there is a change in the speed or the velocity of the light, and because of it, it bends from its original path. This phenomenon is known as refraction of light. So today here in this, we will be studying about reflection of light through spherical mirrors. So let's first see the reflection, what reflection was, which we studied in our 8th standard. Reflection was basically, suppose this is your reflecting surface, right? And this is the incident ray. This light ray get incident at this point on the reflecting surface, right? Then after reflection, it will, after getting incident, it will get reflected to the same medium, right? So this was your incident ray, this is your reflected ray, and if I draw the, a line which is perpendicular to the surface, right? This is perpendicular to the surface, so this is known as normal, right? This normal is a line which is perpendicular to the reflecting surface and is passing through a point at which the light is incident, and this point is known as point of incidence. Now, the angle between the incident ray and the normal, this angle is known as angle of incidence, and the angle between the normal and the reflected ray is known as angle of reflection, right? So, this is our incident ray and this is reflected ray. Angle between incident ray and the normal is known as angle of incidence, and the angle between the reflected ray and the normal is known as the angle of reflection. So there are two laws which is being followed for reflection. The first law says that angle of incidence is always equals to angle of reflection for the case of reflection from even surface, which is known as regular reflection. And second thing is that the incident ray, the reflected ray, and the normal, all the three rays will lie on the same plane. This was the basics of reflection, which we have already studied in our 8th, 9th, 10th standard. Now today what we are going to study is, reflection through the spherical mirror, right? Because mirror is a reflecting surface. So what is spherical mirror? Let's first take a sphere. Suppose this is a sphere, right? This is a sphere, and if I cut small part out of it, two small parts out of it, like this, right? Then what I'm left with is two curved surfaces. The sphere was having its center at this point, right? Now we have two curved surfaces here. Now if I polish this side of this mirror, so that this side of the sphere, this sphere was made up of glass, transparent glass. Now if I polish this side, oh, if I polish, if I polish these sides of the mirror like this, for this mirror, if I, for this part I polish this side, and the other part I polish that side. Then your, the first part, this first part, and let me the second part. So this part of the sphere will work as a convex mirror, and the second part will work as a concave mirror, right? So this is a convex mirror, and this second one is a concave mirror. So what we have seen from here is there's this convex mirror or it is a concave mirror. Both the mirrors are part of a large sphere, right? Now, if it is part of a large sphere, if I draw a line from the surface to the center, similarly here from surface to the center, then this would be the radius, right? This would be the radius. So this distance, the distance from here to the center is known as radius of curvature for the curved mirror and is represented by capital R. So this will be the radius of curvature for this convex mirror, and this will be the radius of curvature for this concave mirror, right? This center, this center was the center of the sphere of which these two mirrors are part. So this center will be known as center of curvature of the spherical mirror, right? This will be known as the center of curvature of two mirrors. Then if I draw a line, if I draw a line this like this, that it passes through a center, sorry, I draw a line like this, which is passing through the center, right? And this is a line, not a line segment, it's a line. Then this line is known as principal axis, right? This line is known as principal axis. So we have seen the center of curvature, we have seen the radius of curvature, we saw principal axis. Now this part, the black part, the curved part is known as the aperture of the mirror. This part is known as the aperture of the mirror. For this part is known as the aperture of the mirror, right? Then suppose we have a convex mirror like this. We have a convex mirror like this. Then the geometrical center of this convex mirror, this geometrical center is known as pole. Is known as pole. This is for a convex mirror. Now, if we see if this is a concave mirror, now this is a concave mirror. So this geometrical center will be the pole of this concave mirror, right? So this is known as the pole. Now let's see principal focus. Now to understand principal's focus, let's draw a concave mirror. Or suppose this is a concave mirror, right? So this will be its pole, and if let's say this is its center of curvature, then if I draw a line which passes from center of curvature, to the pole. Now let's suppose this is the line, okay, and this is the center of curvature C, and this is the pole P. This is center of curvature C, and this is the pole P. Now, when a light ray is incident on the surface and is parallel to the principal axis, let's dot two lines which are parallel to principal axis. There are two rays which are traveling parallel to principal axis. After reflection, what will happen? they will pass to the same point, right? Because they are parallel to principal axis. This incident ray after reflection will pass like this. Now this is incident ray, and again this is the reflected ray. Now both the reflected ray are passing to the same point, and this point where both the light rays after reflection are meeting is known as focus. That is principal focus, represented by capital F. So this is your principal focus. That is, whenever a light ray which is parallel to the principal axis after reflection passes through a point where all other light rays which are parallel to the principal axis are also passing, that point is known as principal focus, right? And the distance between this principal focus and the pole is known as focal length. So remember, focus, the point focus is represented by capital F, and the focal length, that is the distance between the focus and the pole, is represented by small f, that is small distance, right? So this was for a concave mirror. If we need to see the principal focus of a convex mirror, so let's draw a convex mirror first. Suppose this is a convex mirror, right? Now if this is a convex mirror, and let's draw the principal axis first. Let this be the principal axis, and this be the center of curvature. Sorry, not this be the center of curvature. The center of curvature will be here. This is the center of curvature, right? And this is the pole. This is the pole. Now, when a light ray which is parallel to the principal axis get incident, there are two light rays which are getting the parallel to the principal axis and getting incident on this. What will happen? They will reflect in such a manner that it appears as if they are passing to they are coming from the same point. Means this light ray will reflect in this direction, and if this is incident like this light ray will reflect in this direction, right? But after reflection, when we produce them in the backward direction, we find that they appear as if they are coming from the same point. So this point from where they appear to come is known as the focus for a convex mirror, right? So this is the focus, and the distance between the pole and the focus is known as the focal length. So for a convex mirror, this is the focus, and this focus is found when we produce the reflected ray in the backward direction. Therefore, this focus is known as virtual focus also. And in case of a concave mirror, the focus is being formed by actual meeting of the actual reflected rays. Therefore, it is known as real focus, right? So this is basically your principal focus. We were talking about principal focus. Now, what we can see here from the two diagrams is, for a concave mirror, the light rays which were coming from two different points are getting to meet at at one same point, or we can use a word over here which is known as the light rays are getting converged. The light rays are getting converged, and therefore the concave mirror is known as converging mirror, right? Now, if you see in this case of a convex mirror, in this convex mirror, there are two light rays coming from two different points. Then they are getting reflected to two different points which are more far away, right? So here we can say that the light rays are getting diverged, right? They are getting diverged. So the convex mirror is known as your diverging mirror. Diverging mirror, right? So till now, what we see, how this, what we have seen, that is how the spherical mirrors are formed. Center of curvature, radius of curvature, principal axis, principal focus, and your pole, aperture, and center of curvature. Pole, aperture, center of curvature, and focus, principal focus, and your focal length, right? And then also we also saw that how we can say that the concave mirror is known as converging mirror, and convex mirror is known as diverging mirror, right? Now in the next part here, what we are going to see is we are going to see how the images are formed using uh, your these convex mirror and concave mirror. Now before that, we will see the relation between the radius of curvature r, and your focal length f, and that is your radius of curvature is equals to 2 times of focal length. This is the relation which we are going to see, right? So simply, if I draw the ray diagram, that this is a concave mirror and this is the principal axis. This is the principal axis, right? Now suppose a light ray is traveling in such a way that it is parallel to the principal axis. Light ray is traveling that it is parallel to the principal axis, right? So light ray traveling to the principal axis will pass through the focus. So this light ray is passing to the focus. So this is our incident ray, and this is the reflected ray, and this would be the normal, right? This is the normal. So this is the normal. So if this is normal, this is your angle of incidence, and this is your angle of reflection, right? This is angle of incidence, this is angle of reflection, and let this angle be equal to alpha. Let this angle be equal to alpha. So what we can see here is that this incident ray and the principal axis are parallel to each other, and the normal acts as the what? Normal acts as the transverse. Now if normal acts as the transverse, angle of incidence and alpha become equal. So angle of incidence is equals to alpha, and we know that because the reflection is taking place, I is equals to angle r, and from here by parallel lines theorem we can see that angle I is equals to angle alpha, right? Therefore we can say that the these two angle of triangles, let's say this is C, let this be F, and let this be N. So in the triangle CFN, the base angles are equal, and if base angles are equal, then CF will be equals to, let this be the pole P. CF will be equals to FN, because now the triangle CFN become an isosceles triangle. So this side is equals to this side. Now, because the aperture of the mirror is very small, so we can take an assumption that this point P is very close to point N. These point P and point N are very close to each other, so we can take an approximation that Fn is approximately equals to Fp, right? So if we take this approximation, we can also write Cf is approximately equal to Fp, right? Now, what Fp is equals to? Fp is nothing but the focal length. So Cf is equals to what? Again, so Cf becomes equals to focal length. Now, if we see that the length Cp is equals to Cf plus Fp, and Cf is equals to small f, that is focal length, plus Fp is also equals to focal length, and Cp is nothing but the radius of curvature. So here we can write r. So from here we can say that r is equals to 2 times of f, right? So this is how we find the relation that the radius of curvature is 2 times the focal length of a mirror. Same calculations are true for your convex mirror also. Will not get into it. You can just have a practice of it. If you have any doubt, you can comment in the comment box. So we saw that the radius of curvature for a curved mirror, radius of curvature for a curved mirror or spherical mirror is equals to 2 times of focal length, or the focal length of a spherical mirror is equals to half of the radius of curvature, right? I hope this is clear to all. Now, moving forward, we will see how the images are formed using these mirrors. So, before forming the images, we should know some rules which are to be followed. The rules to be followed is, the very first thing we should know is that to form an image, we need at least two rays to get reflected and meet at a point, right? At least two rays to meet at a point, then only the image can be formed. The second thing is, there are two types of image formed. One is a real image and another is a virtual image, right? Virtual image. Real image is the image which is formed when the actually reflected light rays meet at a point and form an image. Whereas the virtual image is formed when the reflected light rays are being produced backward, right? It is being produced by us, that is being produced backward, and we try to meet them at a point, right? So when they meet at a point somewhere backward, that is the point where the image is formed, or it appears to be formed, and that image is known as the virtual image, right? So when the image is formed after producing the reflected ray backward, the image is known as a virtual image. Real image can be obtained on a screen, but virtual image cannot be obtained on a screen. We will see further in the ray diagram. So from there, it will be very clear to you how the virtual images are formed. So the images formed are two types, that is of real image and virtual image, right? Real image and virtual image. So the very first thing is that an image is formed only when the reflected rays meet at a point or they appear to meet at a point. Images formed are of two types, one is of real and another is of virtual type, right? So real image is formed when the actually reflected light rays meet at a point, and virtual image is formed when the reflected light rays are produced backwards and they meet at a point or they appear to meet at a point. Then that ray is known as your, that image is known as your virtual image, right? Now let's see some more rules. The very first rule is, this rule is related to your rays. That is, whenever first ray passing parallel to principal axis, So suppose this is a concave mirror and This is the principal axis. So the rule is that whenever a light ray is traveling parallel to the principal axis, it will always pass through the focus. So this point will be focus. This is your pole, and the center of curvature would be somewhere here, right? So whenever a light ray is traveling parallel to the principal axis, whether it is a concave mirror or a convex mirror, the light ray after reflection will always pass through the focus, right? So this is for a concave mirror. Let me draw for the convex mirror as well. This is for the convex mirror. This is your pole. Center of curvature will be somewhere here. The light ray which is traveling parallel to the principal axis, the light ray would appear as if it is coming from the focus. So the light ray will get reflected in this way, right? Now these dotted lines are being produced backward, and here is the focus. So this reflected ray appears that it is coming from this one, right? So whenever a light ray parallel to the principal axis get reflected, it gets reflected in such a manner that it passes to the principal focus. Second type of ray which we are supposed to use, second type of ray which we are supposed to use is a ray passing through focus. A ray passing through the focus. Now again we'll draw two diagrams for a concave and a convex mirror. So let this be the concave mirror. If this is the concave mirror, principal axis, let this be the pole. Here it would be the center of curvature. Here it be the focus. So if a light ray is passing through the focus and it is getting incident, then after reflection it will travel parallel to the principal axis, right? It will travel parallel to the principal axis. Now we can see for the convex mirror as well. If this is the convex mirror, right? Let this be the principal axis. This is the pole. Here would be somewhere center of curvature. This is focus. So if a light ray is incident in such a manner that it appears as if it is incident at the focus, right? Then after reflection, it will travel parallel to the principal axis. So this is the second ray. Then the third ray is ray incident at pole. Incident at pole, right? So if this is a concave mirror, right? This is the pole. This is the pole. So light ray which is incident on the pole, this will be the angle of incidence. Making same angle, it will get reflected, and this would be the angle of reflection. This is R. So this is how the light ray will get reflected. Now if it is a convex mirror, this would be the principal axis, and here it is the pole. So light ray incident at this pole will get reflected like this with the same angle, right? This I will be equals to this R. Now the fourth ray is your ray passing through center of curvature, passing through the center of curvature. Now, if suppose this is your concave mirror, right, and this is the center of curvature. So, a light ray, if it is passes through the center of curvature, let's say this light ray is passing to center of curvature like this, right? So when a light ray is passing through the center of curvature, it will always be normally incident, and if it is normally incident, it will retrace its path, right? Why it is normally incident? I'll tell you. Let's first see the convex mirror. Then again, this is for a convex mirror. This is the principal axis. This is the center of curvature. So if a light ray which is passing through the center of curvature, it will always be normally incident. Sorry, here is the center of curvature. This is the center of curvature. So if light ray is incident and it is so incident that it appears that it is passing through the center of curvature, then it will retrace its path. So this is for a convex mirror. Now, why a light ray or a line passing through the center of curvature and getting incident on the curved surface is always be perpendicular? Because center of curvature is the center of the sphere of which this mirror is a part, and for a circle, a line drawn from the center to the circumference is known as radius, and that radius is always perpendicular to the tangent drawn from the same point. That is, if suppose this is the curved surface and this is the center, and if I draw a line like this, and from the same point if I draw a tangent, then this would always be equals to 90 degree. So at this point A, let's say the line drawn from the center of curvature is the radius, and a tangent passing through the point A, the radius and the tangent will always be perpendicular to each other, right? So whenever a light ray or a line is passing through the center of curvature and is incident at a point on the curved surface, that line will always be normally incident, or it will be normal to the reflecting surface, right? So we have seen these four rays. These four rays are the rays which we will be using while drawing the images found by the curved mirrors, that is your concave mirror and your convex mirror, also known as the spherical mirrors. So what we have seen till now is that images are formed only when the two reflected light rays meet at a point, or they appear to meet at a point. When they actually meet at a point, they form a real image, and when they appear to meet at a point, they form virtual image. Then we saw four different types of rays which we will be using while forming the image using your concave mirror and the convex mirror, right? So now let's see the image formation using the spherical mirrors. So first we will see the image formation using the concave mirrors. Why concave mirror? Because for concave mirror there are several positions of the object for which we will be forming the images, but for a convex mirror there is only one image formation. So let's start with concave mirror image formation with the concave mirror, right? So very first position is your when object is beyond center of curvature, beyond center of curvature, right? So see here the diagrams which has been drawn by me are not absolutely perfect. They are not at all perfect. They are nowhere close to perfection. But I will be just giving you an idea how the image has been formed. For a perfect diagram, you can refer to the books. There they have drawn with the scale and up to the arc, the straight line. I'm just giving you the idea how the ray travel and how the image has been formed, right? So see, if this is a concave mirror, this is a concave mirror. Let me take principal axis like this. This is the principal axis. Okay, and let me mark this point as center of curvature and this point as your focus. So the object is placed beyond center of curvature. Now when object is placed beyond center of curvature, we will have to take at least two rays which are coming from the object, right? So if this is the object A, B, let this be the first light ray. The first light ray is traveling parallel to the light ray travels parallel to the principal axis, right? And then it will get reflected to the focus. Gets reflected to the focus, right? So this is your incident ray and this is your reflected ray. Now we have to take another ray. So let that ray be a ray which is getting incident at pole, right? So the light ray will get reflected at the same angle. So when the light ray get reflected at the same angle, this is the incident ray and this is the reflected ray. Now the two reflected rays are getting intersected at this point. So the image will be formed here and it will be formed like this. This will be the image and this will be marked as B dash and this is A dash, right? So what we find here is that when an object is placed beyond center of curvature, what is happening? A light ray, we took two light rays, a light ray traveling parallel to the principal axis and that would pass after reflection pass to the focus. Another light ray which is incident at the pole, after reflection again it will pass with the same angle, and these two reflected light rays are getting intersect at a point and we getting an image. So if we write the characteristics of image is, the very first thing is that the image formed is a real image, right? It's a real image. Why it is a real image? Because it is formed because of the two actually reflected light rays intersecting at a point. Then the second thing which we can see is that it is an inverted image, right? It is an inverted image. It is an inverted image. Okay. It is an inverted image, right? Then what we see is its position. Its position is it is formed between center of curvature and focus. It's formed between center of curvature and focus. Now let's talk about its size. If we talk about its size, it is diminished. Diminished means the size has decreased. Now how do we find that the size has been decreased? See, this point is pole and the distance between the object and the pole, this distance is known as object distance and is denoted by small u. Whereas this is the image and the distance between the image and the pole is known as image distance and is denoted by small v, right? So what we find in this diagram is that the object distance is greater than the image distance, right? Or we can say the image distance is smaller than the object distance. Now because the image distance is smaller than the object distance, image size will also be less than object size. That is, I represents the height of the image and O represents the height of the object. So because the image distance is less, height of the image will also be less. Therefore we can say then the image formed is a diminished image, right? So what are the characteristics of the image formed here is, first is it is a real image, the second it is inverted, third it is being formed between the center of curvature, the position is between the center of curvature and the focus, and the fourth thing is it is a diminished image, right? So this was the first position of the object for which we have seen the image. Second position is when the object is second position is when object is at center of curvature. It is at center of curvature, right? So let me try to draw it this way. So this is a concave mirror, right? This is a concave mirror. Let this be the principal axis, right? And the center of curvature would be somewhere here, center of curvature, and let this be the focus. Now the object is at center of curvature. Object is at center of curvature. So this is the object, right? Now let's take the first ray. Again, we'll take the first ray which is traveling parallel to the principal axis. So a light ray which is traveling parallel to the principal axis, right? So this is the incident ray. After reflection, it has to pass through the focus as per the rules which we have seen, right? So light ray, and this is passing through the focus. So this is your reflected ray. This is the reflected ray, right? Now let's take another ray. Let this ray be a ray which is passing through the focus. So this ray is passing through the focus. So a light ray which is passing through the focus after reflection will travel parallel to the principal axis. So this light ray after reflection will travel parallel to the principal axis, right? Now it would not appear parallel to the principal axis, but it will be parallel to the principal axis. As I told, the diagrams which I am drawing here will not be perfect. So now this is the point where the two reflected light rays are meeting. This is the first reflected light ray and this is the second reflected light ray. Now these two reflected light rays are meeting at this point. So the image will be formed here, and this is a point which is just below the center of curvature. So if this was the object A, B, then the image formed will be A dash, B dash, right? This is how the image will be formed. Now, if I write the characteristics of the image formed here is, the very first thing is we can see that the image formed is a real image. Second thing is, again it is inverted, right? Third thing is the image formed is at center of curvature, and fourth is that we have to say the size. What is the size? So this is the object distance, which is nothing but the radius of curvature, because the object is kept at the center of curvature, and this is the image distance, which is again equals to the object distance. Therefore, the because here the image distance and the object distance are equal to each other, therefore the image form will be of same size. Image form will be of same size, right? So when an object is kept at the center of curvature of the mirror, the image will be formed at the center of curvature, and the image form will be real, inverted, and will be of same size. Now let's come to the third position of the object. So the third position of the object is when object is between center of curvature and focus. Object is between center of curvature and focus. So if this is our concave mirror, this is its center, right? This is the concave mirror. Let me draw the mirror. This is the center of curvature somewhere here. So if we draw the principal axis, draw the principal axis. This would be the principal axis. If this is the center of curvature, this would be the focus, and this would be the object. Now, if this is the object, let's take the first ray, the ray which is traveling parallel to the principal axis, right? Ray traveling parallel to the principal axis. This is the incident ray. Another, the ray after reflection will travel passing to the focus, right? Now, if I take an another ray, let so this is a reflecting ray, right? Reflected ray, another ray which is traveling while passing to the focus, right? This is your incident ray. So this after reflection will travel parallel to the principal axis, and it would be somewhat, see again the image formed is not appropriate. So let me do one thing. So this is a concave, this is a concave mirror, right? This is the principal axis. This is the center of curvature. This is focus. This is the object. Light ray traveling parallel to the principal axis. After reflection passes to the focus, right? And another light ray which is passing to the focus. After reflection travels parallel to the principal axis, right? So the image will be formed somewhere here. It is your A dash and B dash. This is your object, so it will be A, B. What we find from here is, if we write the characteristics of the image, again it is a real image. It is a real image and it is inverted and it is formed beyond center of curvature. And if we talk about size, this is the object distance and this is the image distance. What we find is that image distance is greater than the object distance, therefore the image form will be enlarged. That is, the image will be form of larger size as compared to that of the object, right? Now let's see the fourth position of the object. The fourth position of the object will be when the object is at a it as a focus. Fourth position is when object is at focus, right? So when object is at focus, if this is the concave mirror and I draw the concave, sorry, this is the parallel axis, let this be the center of curvature. So this could be the focal length, the focus, and this is the object. So light ray traveling parallel to the principal axis passes through the object, sorry, focus, and a light ray incident at pole get reflected the same angle. And when this diagram drawn appropriately, what we find that these two reflected rays get intersected at infinity, that they are parallel to each other. And when they are parallel to each other, it is assumed that they will intersect at infinity, and because they will intersect at infinity, the image will be formed at infinity. So whenever the object is placed at focus, the image is formed at infinity, and if the object is at infinity, then image is formed at focus, right? When the object is at infinity, the image is formed at focus. Here what we are seeing is that when the object is placed at focus, the image is formed at infinity. This is a ray diagram, and I'm telling you the reverse. If the object as is at infinity, the image will be formed at focus, right? So next image formation is your, we have seen beyond C, we have seen beyond C, we have seen at C, we have seen it between C and F, between F, and now the fifth position is, wait a minute. The next position is your when the object is between F and P. Fifth, fifth is object is between F and P, right? So when object is between F and P, let's see, this is your concave mirror. Let this be the focus and this be the image, sorry, object. This be the object, right? So the first light ray traveling parallel to the principal axis, after reflection it will pass through the focus, and another light ray will be incident at pole, and after reflection it will travel with the same angle. Now again, if it has been drawn with the appropriate scaling, then if we reduce these reflected ray backward, they will meet at a point, and here is the point where the image has been formed, right? Here is the point where the image has been formed. So this image we can see here itself that it is enlarged, but the most important thing is the image here is formed by producing the reflected ray backwards. Now this image is the virtual image. So if I write the characteristics of the image, this image is your virtual image. Second thing is it is erect, it is not inverted, so it is erect. Third thing is it is formed behind the mirror, and the fourth thing is that it is enlarged, right? It is enlarged. Now what we see here is, what we have seen till now is that whenever the images were formed were real, when the images formed were real, two, three, four, yeah, images formed were real, all the images were inverted, all the real images were inverted. But when we find that the image is formed as a virtual image, the image gets erected. What else? We see that the real images are formed at the same side where the object is being placed, but the virtual image is formed behind the mirror. That is, if we place our eye here, right? Now suppose this is the eye. Now if I place my eye here, I will get to see the object. So when we place our eye in the path of the reflected rays, we will get to see the virtual image, right? And that image will be behind the mirror, behind the curved mirror or the spherical mirror. We cannot obtain this image on the screen, but the images which were formed as a real image, that could be obtained on the screen, right? So these are the 5 image formations because of an object placed in front of a concave mirror. Now if we see for a convex mirror, that is the 6th image formation. For a convex mirror, let me draw the convex mirror first. This is the convex mirror. This is the principal axis. Center of curvature would be somewhere here, and the focus is somewhere here. Object is placed in front of the mirror somewhere. The position of the object is not decided, not defined, or we cannot say. It's placed somewhere in front of the mirror. So the light ray first, which is parallel to the principal axis, it will get reflected as if it is passing through the focus. So this will be the reflected ray. Now if this is the reflected ray, the second light ray is your ray which is let's say a ray which is parallel, or you can say is passing it's what you can take it from pole, right? Light ray which is getting incident at pole will get reflected with the same angle, right? Now this light ray when reflected, produced backward, will meet at a point, right? And this point is the point where the image has been formed. This is the point where the image has been formed. So if this is the object and this is the image, we again see that when the reflected light rays are being produced backward, they form the image. So image form is, first thing is virtual. For a convex mirror it is virtual. Now what we see that irrespective of the position of the object, irrespective of the position of the object, we are getting the image as a virtual image. So whatever be the position of the object, we will always get a virtual image, and it would be diminished. It would be diminished, right? So the image formed by a convex mirror, whatever be the position of the object, will always be virtual, and will be diminished, and obviously if it is a virtual image, it will be formed behind the mirror. Behind the mirror, right? So this is the only image formation for what? For your convex mirror, right? This is how the image has been formed. Now, things which are actually very important for this chapter is the thing which is first thing is, now whatever thing I'm going to say from now are very important for this chapter. The very first thing is your sign convention. Sign convention. Sign convention is sign convention is that we will be taking positive sign and negative sign for all the distances which are being measured over here. What are the distances which are being measured over here is, the very first distance which is measured is the focal length f, second distance measured is the object distance, third distance measured is the your image distance, right? So whether the focus is positive or negative, whether the object distance is positive or negative, whether the image distance is positive or negative, this will be decided on the basis of the sign convention. Now, what the sign convention says? Sign convention says that whatever distance is to be measured, either f, u, or v, all the three distances will be measured from P. These are measured from P, that is pole. That is when you are measuring focal length, or when you are measuring object distance, or when you are measuring your image distance, the zero of the scale is to be placed at P, and from P you will be moving towards the focus, or you will be moving towards the object, or you will be moving towards the image, and then the distance will be calculated, right? Now, when the distance has been measured from P, if you are moving, if while measuring, if you are moving in the direction of incident ray, the distance will be taken as positive, and if you are moving in the direction opposite of the incident ray, the distance will be taken as negative. I repeat, when the distance, while measuring the distance from P, if you are moving in the direction of incident ray, the distance measured will be taken as positive, and if you are moving in the direction opposite the direction of incident ray, the distance will be taken as negative, right? And any distance which is being calculated above the principal axis or below the principal axis will always be calculated or be measured from principal axis, right? So distance measured above principal axis from principal axis will be taken as positive, and any distance measured below principal axis starting from principal axis will be taken as negative. So above principal axis is positive, below principal axis is negative. So if I talk about focal length, right? Focal length. If we are talking about focal length, what we saw that for a concave mirror, right? If this was a concave mirror, the light ray get parallel to principal axis and then get reflected at this point, and here it was the focus, right? So, and this is the pole. So while measuring this focal length, I will be moving from pole to focus, and this would be the focal length. So while measuring the focal length, I am moving in the direction opposite of the incident ray. Incident ray is moving from my left to right, whereas while measuring the focal length, I have to move from my right to left. Therefore, mirror, for a concave mirror, focal length is negative. Focal length is negative, right? Focal length is negative. Now, if we talk about for convex mirror, if we talk about convex mirror, this was the convex mirror, and this was the principal axis, center of curvature, and focus was drawn somewhere here because the light ray traveling parallel to the principal axis get reflected like this, as if it is coming from this point. So the focus is drawn at this point. So, and this is the pole. So while measuring the focal length, if I move from pole, I will be moving in this direction, and this direction is similar as the direction of incident ray. Therefore, for a convex mirror, the focal length is positive. Focal length is positive, right? Next, the distance which you are going to measure is, the distance is your, wait for a minute. The distance which you are going to measure is your distance is your object distance. Sorry. Yeah. Object distance, U. If we talk about object distance in all the image formation, what we found that always the object was placed at the left and the incident ray was moving towards the mirror, that is towards the right. And it's obvious that the incident ray are getting are being produced or being they are moving from the object, so they will be moving in the direction actually moving in the direction towards the mirror. So see, if this is a concave mirror and here is the object, incident ray will move in this direction and here is the pole. So to measure the object distance, I have to move from pole to object. So this measurement will be done in the direction opposite to the direction of the incident ray, right? Whether it is a convex mirror or a concave mirror. For this is for a concave mirror and now this is for a convex mirror, right? Now here is the object, this is the incident ray, this is the pole. So to measure the object distance, again I will have to move in this direction. So what we find here is that whether it is a concave mirror or a convex mirror, object distance will be negative always. It will be negative always, right? Object distance will always be negative. Now let me take help of the ray diagrams which I have drawn for your image distance. Now see, all the real images are formed at the same side where the object is. All the real images are formed at the same side where the object is. And when it comes to the virtual image, the virtual image is formed behind the mirror. So from here what we conclude is, if we talk about the image distance V, so image distance is for real images. For real images, the image distance is negative, whereas for virtual images, the image distance is positive, right? The image distance is positive. So, when we talk about image distance in case of mirrors, for real image, the image distance will be negative. For virtual image, the image distance will be positive. So, this is the sign convention. Now, for erect images, the images are, if we talk about the image height and object height. So see, objects are always standing upright above the principal axis. So object height O will always be taken as positive, right? Because the height is above the principal axis. But if we talk about the image height, now again all the images formed, real images, are inverted. So we have to measure it below the principal axis. So for if we talk about image height, for real images, the real images I will be negative, and for virtual images, because virtual images are erect, therefore for virtual images, image height, that is I, will be positive. Image height will be positive, right? So this is what is sign convention. Sign convention says that all the distances measured should be measured from pole, right? And if while measuring the distance we are moving in the direction of in the direction of incident ray, then the distance measured will be positive. And if we are moving in the direction opposite the direction of incident ray, then the distance measured will be negative. Any distance measured above principal axis will be positive. Any distance measured below the principal axis will be taken as negative. Focal length for a concave mirror is negative, whereas for a convex mirror it is positive. Object distance is always negative. If we talk about the image distance is negative for real images, positive for virtual images. If we talk about object height is always positive if we are taking above the principal axis, and image height will be negative for real images and positive for virtual images. This is what is what is your sign convention. Next comes your linear magnification. Linear magnification, right? Linear magnification is denoted by small m, and linear magnification is basically the ratio of the image height to the object height. right? Image height to the object height. Now, if linear magnification comes greater than 1, then the image formed is enlarged, right? If image form linear magnification comes less than 1, then the image form is diminished, right? When m, that is linear magnification, comes equals to 1, then it is of same size. Then the image formed is of same size, right? Now, what we saw was object height was always positive, but if we talk about image height for real image, it was image height was negative, and for virtual image it was positive, right? So if we talk about linear magnification for the case of real image, for the case of real image, I will be negative and O will be positive, giving us a negative linear magnification, which means the image form is an inverted image. So what you conclude is, if magnification is negative, then the image formed is a real image. If the linear magnification for a mirror is negative, the image formed is real image. Now if I talk about the virtual image, in case of virtual image, m is equals to what? I will be positive and O will also be positive, which will give you a result as a positive and means erect, right? So if magnification is positive, linear magnification is positive, then the image formed is a virtual image, right? Now there is one more relation for linear magnification. For linear magnification is also written as minus v upon u, where v is the image distance and u is the object distance. Now let's see whether what we have seen above is true or not. What we have seen is, for real images, magnification is coming as negative. So for what we have seen is, your object distance is negative always. Object distance is negative always, where image distance is, for real it is negative, and for virtual it is positive, right? So if we talk about real image formation, magnification is equals to minus v upon u. So v is, for real image, is negative, and u is always negative. So this would result in a negative. Therefore, for real image, magnification is coming negative here also, using the formula linear magnification m is equals to minus v upon u. And if we talk about virtual image, for virtual image, linear magnification will be again minus v. V for virtual is positive upon u. U is always negative. So this fraction would result in negative, and this negative and negative becomes positive. So our answer will be positive. So here also what we see, that the magnification for virtual image from the formula minus v upon u is also coming as positive, right? So magnification is positive, linear magnification is positive, then the image formed is virtual, and if linear magnification is negative, the image formed is real, right? Now one more formula for linear magnification. For linear magnification, m is equals to f minus v upon f, and is also equals to f upon f minus u, right? These two formulae are also important for linear magnification. What else we have seen is, linear magnification is equals to I upon O and is equals to minus V upon U, minus V upon U, right? Minus V upon U. So these are the formula for the linear magnification, and these formulae will be used for your numericals. Finally, the formula which is most important formula here, that formula is your mirror formula. For Neet, the derivation is not important, so I simply give you the formula. The formula is 1 by f is equals to 1 by v plus 1 by u. 1 by v plus 1 by u. This is the mirror formula, which is the relation between f, v and u. Whenever you are solving the numerical, always put the value of f, v and u with the sign convention. Suppose in the question they say that an image is formed with something something, and the mirror used is a concave mirror of focal length 20 centimeter. So you always will write focal length is equals to, because it is a concave mirror, you will always write f is equals to minus 20 centimeter, and you will be putting the value here as minus 20 centimeter, right? And they say that it forms a real image at a distance of 10 centimeter from the image, from the mirror. So the image distance will be equals to minus 10 centimeter, because real image is has image distance as negative. And suppose the object was placed at a distance of 5 centimeter from mirror, so the object distance will be equals to minus 5 centimeter from the mirror, that is object distance will be minus 5 centimeter, because object distance is always negative. Suppose the things were same, but the image found was a real image, virtual image, then the image distance will be written as v is equals to plus 10 centimeter, right? The mirror is a concave mirror, minus 20 centimeter focal length, and the object distance is minus 5 centimeter. But because the image formed is a virtual image, therefore v, that is the image distance, will be taken as positive, right? I hope you understood how the sign convention is to be taken while putting the values in the mirror formula, right? So this is what you have to study for your reflection through curved surfaces, right? So I hope the things were made very clear to you all. Please go through the lecture, and if you find something missing in this, or if you do not understand anything, please comment in the comment box, and please go through all each and every details in this, and I'll be waiting for your comments in the comment box and your feedback from your side, so that I can improve the things, or bring more things into the lectures, right? So please do put your comments in the comment box. This was all from my side. Thank you.